Welcome, everybody. It's a great pleasure to introduce Professor Andrea Roli from the Università di Bologna. Professor Roli has a long collaboration with the University of Brussels. It's almost 20 years that he's, or maybe more than 20 years, 24 years, that he's collaborating with the lab Iridia of the ULB. He's here this time thanks to an international chair and is a guest of BrIAS. And Professor Roli is working mostly in complex systems, and recently he started being more and more interested in robotics. And so I see that the presentation of today is going to focus on the topic of robotics. So, Andrea, welcome.
Thank you very much. I'm very glad to be here. The occasion for this talk was for me a way to reconsider, rethink in a single stream what I've done in the last years. I would say last 5 years, more or less. And so what I'd like to present you to talk about today is a perspective that has its roots in cybernetics, but leads to the possibility of designing artificial systems, mainly artificial systems that interact with the real world, with the physical world, so robots, by taking inspiration from some principles that actually were first proposed in the field of cybernetics. And then, of course, I will show you results that I've recently obtained in this view, in this perspective. This is, of course, not a work that I have undertaken alone. The main collaborators in this are Stuart Kaufman and Johannes Jäger, mainly for the discussions concerning agency, artificial intelligence, artificial life, and the relation between organisms, living organisms, and artificial systems, and work done in robotics in collaboration with Michele Braccini and Paolo Baldini. So there is a research question behind this work, and it is not a new research question. It's something that is in the area of cybernetics and AI and artificial life since many years, and it concerns the possibility of formulating basic and general principles that we can identify to describe the evolution of living organisms and the design of artificial systems and their way to adapt in the world. So in particular, there is an objective that is of identifying a minimal set of properties that can be useful for that. And actually the implications of this would be twofold. The first one is that we have now, if we identify these principles, we can discuss more precisely where is the boundary, or if there is a boundary, and in case what is its shape between organisms and artificial systems. And in these recent times, the discussion about artificial intelligence and natural intelligence is particularly treated also in the newspapers, and it's something that we have to address in a principled way. And then the second implication is that if we can identify these principles, we can probably or hopefully apply them in the design of artificial systems. So this talk is basically divided in two parts. In the first part, I will provide an outlook of the principles that I think are relevant from cybernetics also to today activities in robotics. And in the second part, I will illustrate the results in which I'm involved and that build upon those principles. So if we talk about cybernetics, let's have a brief recap of its aims. There's a nice paper by Eiligen introducing cybernetics, which is usually divided historically in two periods, first cybernetics and second cybernetics, while now we basically conflate all the principles that came in that period. And you see, the aim of cybernetics is to describe how systems, natural or artificial, can use information models and how they use these structures to decide their actions in order to act in their world and carry on a task and keep on carrying on this task in front of perturbations. The original objective was indeed to explore the similarities or the differences between natural and artificial systems. So it's a question that dates back to the first half of the 20th century, and we are still improving and working on that. And as Eiligen writes in this paper, there are some principles that were clearly stated in the first books, in the first publications of the cybernetic scholars, that were then, for some reasons, socio-cultural reasons, somehow forgot and rediscovered in different fields. And we will see in what I'm going to tell you now in the first part of the talk that there are indeed some ideas that now have probably different names, but they are exactly the same, conceptually wise. Now, the second important word in the title is adaptivity. For that, I rely on the definition of adaptivity by Rolf Pfeiffer in his famous book, Understanding Intelligence. And he defines this as the ability to adjust oneself, so the system, to the environment, which is a very general and, if you want, vague definition. But it's very useful to introduce what cyberneticians thought about adaptivity. And it's important to distinguish between several kinds of adaptivity. So we can have evolutionary adaptivity, which is the kind of adaptivity that species undergo. So it's a kind of phylogenetic process in which a species can adapt to the environment. The environment can be, of course, composed of other species, so there's a kind of coevolution. But in evolutionary adaptivity, what is important is that we do not have an adaptation of a single individual, of a single organism during its life, but it's just a matter of evolution of a species, so a group in time, in the years. Then we have physiological adaptation, which is a kind of adaptation that takes place by means of processes in the organism or in the system, like sweating, for example, to lower the temperature in animals. There is sensory adaptation, which is something that takes place in a specific sensor and adapts the way the sensor can react to changes in the environment. For example, we can adjust our capability of detecting objects in the space depending on the light that we receive. And of course, there is adaptation or adaptivity by learning, which is probably the broadest area of adaptivity, which is exactly the one that was addressed by one of the founders of cybernetics, Ross Ashby, in a beautiful book called Design for a Brain, 1960. And the aim of Ashby in that book was indeed to detect the mechanisms that we can observe in organisms with a neural, with a nervous system, so with a neural part, in order to adapt their actions to the environment. And in fact, what he says is that he's interested not in inborn behaviors, so reflexes or something similar, but in that kind of learning that he calls adaptation, that has the effect of modifying some part of the organism or the system in order to let it react differently to the conditions in the environment. And this, as Ashby remarks, is modified markedly by the organism's individual experience. So there's this clear reference to the history of in the life of the organism, and so it's the path dependence of the reactions of this individual during its life to the conditions. And Ashby goes further in this, and he introduces a concept that is somehow analog to the concept of homeostasis. But he simplifies this in the sense that he provides a simple model for that, saying that a behavior is adaptive if the organism, the system, is capable of changing something of its dynamics in such a way that some essential variables are kept inside a physiological limit. This, of course, is inspired by homeostasis, but actually what he did was that he generalized also this notion in the sense that we do not require that a system is simply capable of keeping some essential variables, so essential values on which its life depends, keeping them inside a given range, but the point is that the individual can also act such that the conditions around it can be better to keep those values inside the range, and even more, that there is a notion of getting something better with respect to some utility functions. So it is not just a constraint that is satisfied or not, but it is a condition that can be better or worse. And the principles of adaptivity, as proposed by Ashby, tries to put the organism, the system, in the condition of having even better conditions. So we see that what we call now adaptivity in terms of adaptivity by learning is actually what Ashby defined, with the difference that we now often use not essential variables, but specific utility functions to identify the conditions for the organism to adapt. And usually these functions, as we program robots, are defined in advance by the designer. So they are not, they do not grow inside the organism. They do not depend on organismic agency as in living organisms. There is another fundamental point that was stated by cyberneticians, and here I cite von Foerster, who's the main exponent of the main scholar of the so-called second order cybernetics, because he clearly introduces the presence of an observer in the discussion. But what I want to remark is that he clearly states that the initial name, the initial meaning for cybernetics was not the one that Wiener used in his famous book, so the control and communication in the element and the machine. But the point was that, according to von Foerster, the original idea of cybernetics was to focus on circular causality. So we have systems that interact with the environment, and there are several feedbacks that connect, so loops that connect the system with its environment. And it is in that relation given by the feedbacks that we can exploit some mechanisms for adaptation. And it is exactly what we do now in robotics according to the a general approach in which the behavior of a robot is not inside and just, we do not find the original cause for the behavior of a robot just inside its control program, but the dynamics of the robot, the behavior of the robot depends on an intertwined interaction among its control program, its body, so its chassis, its sensors, its actuators, and the environment, the properties of the environment. And so we can, in principle, say that the behavior of a robot is in general emergent in the sense that it is produced by the interplay between these three factors. And more in particular, when we focus on cybernetic concepts inside robotics, we usually outline a specific circular causal loop, which is the so-called sensory motor loop. That can be easily explained in the fact that what a robot perceives comes to the robot through its sensors, but the actions that the robot takes are also influencing the way it perceives the following data coming through its sensors. And of course, there is a feedback in this, there is a loop, because the actions the robot takes depends on what it perceives, and what it perceives depends on the action it takes. And it is really exploiting this loop that many robotic systems are designed. But this is not a new statement. This actually comes from cybernetics. And in fact, I'd like to just briefly illustrate what is called the double feedback model, or the ultra-stable model proposed by Ashby, which reminds, in a very close way, the models we use now to control robots. So we have a robot in the orange rectangle that is composed of its body, its actuators, and its sensors. So it acts on the environment by using the actuators, and it perceives information through its sensors. And these information come from the environment. The behavior of this robot is controlled by a control software that we can, in abstract terms, consider as dependent on some set of parameters S. The environment actually acts on some essential variables. You see that specific clock means that we have some variables that have to be in a given range. This is the original draw by Ashby. But what we can just say is that the essential variable are a placeholder for a utility function. So they mean that the utility function is influenced by some property of the environment. And by observing this, we can adapt by changing some parameters of the system. There you see a little green square, because in that arrow, thick arrow that Ashby draws in this scheme, inside that there are all the mechanisms that we can design for adaptation. So it is not a minor point. And I have to say that while Ashby mentioned simple trial and error and also some kind of artificial evolution, we are now currently exploring several mechanisms for adaptation. So it's basically in that square that we can introduce some novelty in this general scheme. But it's important to remark here that the environment acts on the system both by through the sensors of the robot and also by acting externally to the utility function. And this is something that has to be taken into account while designing systems, that the robot is influenced by properties that might not be perceived directly, but just indirectly detected by the effect on the essential variables or utility function. Now a final statement that I think is extremely important that comes from cybernetics, and I'm mentioning the electrochemical devices by Gordon Pask. Gordon Pask had the idea of designing physical systems in which the specific interaction with the environment was not defined in advance. But the system itself should self-organize, and I will be clearer in a moment about what kind of self-organization Pask is referring to, in such a way that relevant stimuli from the environment could be detected. This has a profound implication in our view on evolution, on natural evolution. If we think of natural evolution and the way organs, and especially sensing organs, evolved, there is a parallelism with this kind of self-organizing adaptive device by Pask, in the sense that sensing organs evolved because they mean something for the organism, so they provide some relevant information for the organism to survive. And they have been developed in the several steps of evolution in organisms because they provided relevant information for the survival. And so they basically co-adapted, co-evolved with the environment. And Pask actually aimed at providing a concrete example of this, not in terms of evolution, but in terms of adaptivity in the real world. He made several experiments, and the general idea was to have a dish with some iron salt in water or oil or other liquids, and the particles of this salt were able to form threads as a response to, I go back slightly, as a response to the stimulation exerted by some electrodes and the current that flows along these the threads that are created here depends actually on the way the very threads create. So it's a kind of mechanism that reinforces the threads that carry the highest quantity of current, and so it basically dilutes the ones that are not able to do that. So it's a kind of positive feedback. And the results were that these systems, just with this positive feedback mechanisms, were able to detect and to distinguish between different frequencies. And in fact, there's a nice paper by Peter Cariani, who's summarizing the work by Pask, that talks about the construction of an ear, which is evocative, but the point is these devices were able to detect what is relevant in that condition for the system. Then they, of course, structures are stable unless something in the environment changes, and so they can recreate. Well, the legacy of Pask is what is called now epistemic autonomy. So the kind of autonomy that a system can exhibit in terms of being able to detect what is the piece of information that is relevant for its working, its utility function. And there's a thorough discussion about epistemic autonomy that we can find in the papers by Peter Cariani. But it's important, one of his, I mean, many sentences, but especially one that is an inspiration for the construction of artificial systems now, which is the third one here. And these devices, so devices that are able to detect what is relevant for them, so adapt or even change their sensors in order to get important and relevant information for their survival in that particular moment, are particularly useful when we cannot anticipate what are the conditions in which the system will work. And of course, this introduces an enormous challenge, because we usually, as engineers, I'm an engineer, we define in advance what is the environment, what are the properties of the environment in which the robot has to work. And this is absolutely fundamental to have reliable robotic systems. But if you want to explore also the boundary of this, I think we have somehow to relax part of these constraints and trying to see whether there are not completely open conditions, but somehow slightly less predefined, in which we can find place for adaptivity in this sense, given a flavor of epistemic autonomy. In fact, it is not possible to have true epistemic autonomy unless we have a process of evolution of devices that take information from the environment. For the moment, we don't have this technology, but we can do some step towards it. And this is in the second part of the talk, which is approaching. But the idea is that once we recognize that it is in the interaction between the organism or the system and the environment that we find the emergence of this epistemic autonomy. So it is exactly in that interaction that the organism, the system, should find the meanings of information retrieved through sensors or the actions that it takes. It is there that we can model some part of adaptation in such a way that you can probably go towards epistemic autonomy. And now I'd like to show you some results in this direction. As I said, we have not now a technology that, or I'm not working on a technology that provides a direct adaptation of the devices or the sensors. But what we can do, this is the inspiring idea that I've just mentioned, but what we can do is going slightly in that direction. And what are the aims of that? So why do I seek epistemic autonomy? Do I really need it? Well, I think there are conditions in which this may bring some advantages. And of course, one concerns the possibility for a robot to adapt while it is working in an environment. So to adapt its behavior, parts of its behavior. If the robot is carrying on a task, then maybe for some damage, lights turns off, and the robot should be able to carry on this task anyway. A second important point is that robots might be damaged. There might be faults or damages, and we'd like the robot to be able to carry on this task, maybe with a smaller efficiency, but still continuing its work. And a third important point is that there are models trying to capture the essence of adaptivity in organisms and to compare adaptivity of organisms with the possible adaptivity of artificial systems. And by working on that part, so the interaction between the system and the environment, we can provide an experimental setting also for testing these models. As we don't have now the possibility of evolving sensors and actuators, there are still some approaches that provide, let's say, a viable way to address this problem. One has been already tested since years, and it is morphological computing, so a way of letting some material carry on some part of the dynamics of a system that was previously performed by computing. So, for example, there are artificial tendons and muscles that can be used in robots, and they have a behavior that depends only on the material on the properties of the material, the physical properties of the material, and so they are not controlled by servo mechanisms, and we don't have to care about the computation of that part. Another interesting approach is evolution in materia, which is a recent approach. I say recent, but the first publications were around, I think, 2015, and it concerns the use of specific materials that can receive some inputs from the external, and depending on these inputs, these materials can provide different kinds of dynamics. So the idea of evolution in materia is to find, by means of artificial evolution, the proper control signals to send to this material in such a way that the material produces the desired behavior. One of the typical applications of that is in reservoir computing. So we have this material that is controlled in such a way that it can classify different input data. And a third approach, which is the one I will talk about, concerns the possibility of adapting the connections between sensors and the control program of a robot, and between the control program of the robot and the actuators. So if I cannot modify the sensors and the actuators that are provided with the robot, what I can do is to let the control program of the robot decide where these, to what extent the information that is coming from the sensors can be used, and in terms of information that is received by the environment, and also how this information can be translated into actions. So what we could do is to let this part be subject of adaptation during the life of the robot. And for these experiments, the idea is to have not a control program written in a general purpose language or high-level language, but a network controller of several kinds. I will mention you a couple of examples. And in this way, it's rather easy to define the coupling between sensors and the control system of the robot, which are just nodes of the networks. And the adaptation mechanism can be of several kinds, but the idea is that during the life of the robot, there are epochs in which the robot can test new connections to the network, from sensors to nodes, and from nodes to actuators. So to be more precise, the idea is that the robot is controlled by a network of some kind, and some nodes of the network receive a value that is imposed from the external coming from the sensors, and other nodes, so-called output nodes provide a value that is used to control the actuators. So, for example, these are nodes receiving information from light and proximity sensors, and these nodes are used to control the wheels of the robot. What is important here is that the mapping from sensors to nodes of the network, so to input nodes, is not predefined, but this has to be found by the robot during its action in the physical world. And the same holds for, in principle, for the actuators. So the output nodes are not defined beforehand, but they will be changed by the adaptation mechanism and used to control the actuators. What is the intuition of that? If I have a network that provides a sufficiently rich repertoire of dynamics, so I have a dynamical system, by coupling this system with the values that come from sensors and by controlling actuators with the outputs of this system, but these actions that are performed via the actuators by means of this of the loop I mentioned before have an effect also on the sensing capabilities of the robot. What we have here is that we'd like to shape the dynamics of this dynamical system that is controlling the robot in such a way that the dynamics will be suitable for carrying on a specific task that we want the robot is achieving. So in general, the idea is to shape the dynamics, to let a system learn what are the proper connections, suitable connections, to shape the dynamics of its control system in such a way that the final behavior meet some goals or tends to maximize a utility function. So in our experiments, we first used random Boolean networks. Boolean networks are networks studied initially that were introduced to study the genetic dynamics inside a cell, but they are classical computational systems. And random Boolean networks are random graphs in which nodes are controlled by Boolean functions. So they are basically a random mass of nodes and wires, but they can be tuned in such a way that depending on the kind of functions that we use and the density of connections, we can have networks that have a dynamics, that exhibit a dynamics that is at the edge of chaos. So it is critical in the sense that it can provide a behavior that is a mixture of order and disorder behaviors. There's a wide literature on the properties of critical systems, which I'm not talking about now. What matters for this presentation is that we are now considering a system that exhibit dynamics that are reliable in the sense that they do not fluctuate abruptly in case of slight and minor changes in the environment, but still they provide different kinds, they can provide different kinds of dynamics. So by using these networks, I'm now summarizing the results of recent publications. We addressed the problem of adapting a robot controlled by a Boolean network in 3 different tasks of increasing complexity or increasing difficulty. The first one is collision avoidance. The second one is collision avoidance, but preference with a specific area in the environment. as you see here. And the second and the third one is the transportation of objects from an area of the arena to the other one, back and forth. Here you see groups of robots, but actually the behavior is individual. So we performed these tasks with the experiments by using groups of robots because they provide a glance, let's say, of a dynamic situation in the environment, because they have to avoid collisions among themselves, but there is no swarm behavior here. So yeah, we are interested in individual behavior. What I didn't mention so far is that the evaluation function or utility function that the robot has to optimize or maximize depends only on the information it can get through its sensors in its condition. So we don't have any, and this is a strict requirement if I want to consider online adaptation of a robot that is let alone in a system. The only information it can get comes via its sensors. So, or it's a kind of integration of the values that can come from its sensors, but there are no other sources of information that come from the external or from an external critic. So in this sense, all the capability of evaluation that a robot has depends on the information it can get through its sensors in that particular case or interval in the environment. So we made experiments only in simulation so far. First of all, it was not expected that this should work. Basically, it was a high expectation, but we were not sure. But in fact, it worked. Here I just wrote an average percentage of the cases in which it worked. We made many replicas of the experiments, so depending on the case, 100 or 1,000. And in general, we have a very high fraction of working cases. So this means that when the dynamics of the network is sufficiently rich, this adaptive mechanism is able to find the proper connections, sensor nodes and nodes actuators, in such a way that the robot can carry on this task. Moreover, we introduced noise in the environment, and the robots were still able to carry on their task. And finally, this is one of my favorite subjects in complex systems, the advantage of being critical. We compared the behavior of robots controlled by critical networks with the other two cases, so ordered networks and so-called chaotic networks, let's call them disordered networks, and the behavior was clearly better if the network was critical. And this is let's say, a further piece of evidence that critical systems have an advantage in adaptation, not just in evolution. But the results do not stop here. We made, and here there's the contribution of Paolo, we made similar experiments by using not Boolean networks, but nanowire networks, which are based off nanotubes that are randomly placed in a plate, and the intersections of these nanotubes provide a junction. And in this way, we create a network that can be traversed by a current. And we use the same general idea with experimenting, and also experimenting with different adaptation mechanisms, because in the previous case, they were just basically trial and error. So try a connection. If it doesn't work, try another one, slightly changed. And in these experiments, we were more systematic in trying different adaptive mechanisms. And also in these cases, we found working robots, also in a task that requires memory, that is the T-maze task, in which the robot receives a piece of information about a final direction to take, but this information is given just for an interval of time. So the robot should store this information and learn where to go, if going left or right. But this depends on the epochs. So the robot has to be able to distinguish between left and right by means of this piece of information and remember this to achieve the task. So this was quite interesting. Another step concerns the, as I mentioned, the case of behavior of robots in face of possible damages. So we tried the same, in the same environment with a different task, in this case phototaxis, a simple phototaxis behavior. What happens if we provide the robot with faulty sensors? So we decided to damage part of these sensors. We consider a robot with a sensor in a circular placement around the robot, and we artificially introduced damages and faults in portions of these sensors that they could be detached, so don't take place to the dynamics, don't intervene on the dynamics of the network controlling the robot. We can set permanently to a random value, which is something different and something that happens with the devices, or they can provide a source of random noise that changes every instant in time. And despite this, we observed that the robot, by means of these adaptive mechanisms, is able to carry on this task, usually by increasing the number of faulty sensors, the performance degrades. But here we have a graph simply representing the percentage of successful robots achieving the task successfully. And it is interesting to note that among the 24 sensors, if we use all of them, we reach this value of at the end of the simulation. But if we damage slightly more sensors, so not 0, but 3 or 6, we have even better behavior. This might be an indication that sometimes the amount of information might be too much, and the system has to learn what is actually the relevant information to be used. So too much information can somehow be an overload on the computational part of the system, while providing less information might be beneficial, but this is, of course, to be investigated. And of course, if we damage more sensors, the performance decreases. But still, with some interesting results, because it's a kind of graceful degradation. Now, there are several issues to be tackled, because these are the results of preliminary experiments done in simulation and with simple mechanisms. But we have to take into account that there are several issues in online adaptation. First of all, the evaluation that the robot can make about its performance depends on the current state, and not just the state, but the history of its actions. So it means that whenever we evaluate the robot, we don't evaluate the robot in the same conditions at which we have evaluated it before. And this introduces an enormous, let's call it stochasticity, but it's an enormous unknown factor to be controlled. And I have to admit that this was one of the reasons I was not sure the experiments we made could have provided positive results. But of course, we have tested the robots in conditions in which it is true that states are different and the positions, the place of the robot is different, but still the environment does not change much. The second point is that only situated utility functions can be used, because I cannot intervene on the knowledge that the robot has. Otherwise, I cannot claim it's autonomous in finding its adaptation to the environment. And this poses big limitations in the approach, while probably by recalling the suggestion made by Ashby using essential variables, so the equivalent of the concept of homeostasis, we may have some proxy of these functions. So I'm not evaluating the behavior of the robot, but I'm putting the robot in a condition in which it has to survive, it must survive, and it has to find the actions for its capability of surviving. And surviving might mean to find a place to recharge and to clean the environment and so forth. Then a third important issue. If I let the robot free to do whatever it wants, it's a guarantee that the robot, after a while, will take an action that destroys it. So I have to put the robot in controlled conditions and avoid the ones that can break the robot without possibility of recovering it. Not just because I don't want to lose a robot in the lab, but because I want the robot can test possible behaviors in a confined environment, as we usually do in child education. So we prefer, or learning, we prefer a child to learn what to do, but in a confined environment, in a confined condition, not trying whatever it can be. And a fourth point, which is somehow less critical than the first three, is that usually for adaptive systems of this kind, we have to wait time before they are able to adapt. So the outcome of an adaptation process should be controlled in such a way that it takes place in a useful interval of time with respect to the task that the robot has to carry on. And these are really important issues that we are trying to face now. There is an ongoing work on different paths. One is to consider several kinds of adaptation in the controller of the system. So we can control the connections, as I showed you before. We can control parameters of the control program. We can use higher level ways of combining behaviors in the robot, and we can apply these techniques to combine these behaviors. Also, the adaptation mechanisms, the green square that I've mentioned concerning the PASC ultra-stable system can be changed and can be, of course, something better than trial and test. An idea could be to use classical theories in learning, for example, non-associative and associative learnings, habituation, sensitizations, and so forth, as ingredients for these mechanisms for adaptation. And I've already mentioned the possibility of combining simple behaviors, which is one of the tasks we would like to address, and we are currently addressing. And also, the final application, which I think is rather promising, is try to apply these several mechanisms and strategies for adapting in case in which the robot has to face damages and recover from damages, or actually be able to adapt its behavior in such a way that despite these damages, at least part of the work can be still carried on. And this is probably one of the main areas in robotics which require further advancements. There are some results from different perspectives, but still there's large room for improvements. And with this, I conclude my talk, and I thank you for your attention, for being here.
Thank you, Andrea, for this very nice talk. Very clear, very interesting. And it definitely raises a huge amount of issues. Any question from the audience? I have a question to start. You mentioned a number of forms of adaptations. One was a collective evolution, and the other were individuals. I think that among the possible collective form of adaptation, we have also social and cultural adaptation. So I imagine the emergence of communication protocols, the emergence of a language. So I imagine a society of individuals that adapt to the specific environment by changing the way they interact with each other. Does this fit into the framework of your reasoning?
I move here to be close to the microphone. Definitely yes. Yes. I didn't mention it because I prefer to keep, let's say, a low profile in this, but definitely this fits in this framework, especially the emergence of language. But this is, let's say, a big area to be explored, but it fits with this. And I take this your question as an occasion to be precise in one of the things I've said about evolution. These forms of adaptivity, of course, are not to be taken just alone individually, so we can have evolutionary adaptivity plus learning, of course. This, I didn't mention, of course, the possibility of combining them. But social and cultural are even other kinds that, of course, can be combined. Yes.
Do we have time for an extra question? I would ask one. So it's fun because it's so long that we're working together, but we keep interacting and asking questions, and every time we have the chance to meet, there is something new to discuss. That's really very nice. So if I take the lessons from cybernetics to the letter and I push it to the extreme, I necessarily take a holistic and systemic point of view. And eventually, I feel like blurring the boundary between the self, the system, and the environment. To really explore the complex interactions between these elements. And so eventually, I feel like thinking that a way of adapting is also modifying the environment. And so I think, for instance, of stigmergy. Stigmergy, to me, and this connects to the previous question, is a way in which individuals modify the environment, and by modifying the environment, they adapt. And this, if you push this even further, you have the possibility of completely changing the environment to fit your needs. It's a form of adaptation, if you want. And this raises an issue because it puts on the table the question the issue of sustainability, if you want. So you modify the environment, but to what extent this modification of the environment is sustainable? Likely you share the environment with other actors, so what is the impact of this modification on these other actors and so on? So do you feel that again these questions can be handled in your framework? Can you imagine a system that is able to modify the environment to fit its purposes, yet assess the long-term implications of these modifications?
It's a tough question. Well, first of all, you're right in the sense that saying that if we take these principles to the limit, we have to consider also the fact that the environment is part of the dynamics concerning the system, and Ashby himself wrote that systems can change something in the environment so that their form of adaptation do not concern the organisms or the system alone, or even couldn't touch it, but the system can act in the environment such to adapt it to its needs. And concerning sustainability, this I think poses, it's an opportunity for that, for sure, but there are some issues in the sense that now I'm here, I speak with the influence of Stuart Kaufman in reasoning about this. If we let systems to adapt in the way organisms do, we lose the possibility of predictions. Not just because we have imprecisions or errors in the measurements, and then our models, of course, are affected by errors. But if I wait time enough, let's consider evolution, an evolutionary process, then something can happen or appear that was not in the variables of a model that I could provide at the beginning. So new variables come in, and these are completely new. So I have new things to include in my model, and I cannot predict them. So in this sense, I'm talking about epistemic autonomy and systems that are equipped with some kind of autonomy, and also autonomy to change the environment in case we find ways to do that. But I'm really afraid of letting them free to do what they want. Because we are responsible also for the actions that an autonomous artificial system will take. So in case of sustainability, I know what are the limits of the current adaptive systems. I'm not worried about them. But it's not impossible to reach a technological level at which these might have some kind of autonomy. And I think we have to somehow contain their capabilities to change the environment, to use the environment, and to modify it. Because they can provide, they can build or create situations that are not possible to be predicted in advance. Especially if they use in the environment natural resources, or let's say the environment, the natural environment. And in this sense, I think we are we have to feel this deep sense of responsibility in the technology we use and we design. And just to quote Kaufman, we are in nature, not above nature. So we are part of that, and all our artifacts carry on our responsibility of their behavior.
Thanks, Andrea.
Thank you, Mark.
I think that any question? Fantastic.
Okay.
I'm interested in your control method. I mean, you said you used the network control. I mean, what's the
Could you please come here for
That's fantastic.
ah.
We have a microphone.
Just one.
Just take.
Excellent.
Thank you.
Thank you. I mean, I mean you mean the network control for the robot. I mean, what exactly control method or control technique you resolved you solved your robot? I mean, maybe you have some uncertainty or some noise or some disturbance. So I mean, you can use the sliding motor control or something else. So what's the exactly? And another question is the network control related to the neural network? I mean, some learning algorithm have been used to the control method, something like the deep learning or the reinforcement learning control algorithm. So I mean, what exactly the control method you used for the network control?
Okay, thank you for the question. I skipped the details of that. The main idea is the following, that we have, let's consider the case of Boolean networks. So we have nodes providing an output that is Boolean, and there is an update function that is a Boolean function of the values that come from input nodes to that particular node. And we update this network synchronously. So we have instant in time in which we update all the nodes at the same time, and these nodes change value. The point here is that we do not have a classical training situation in which we can apply usual techniques. The main reason is that we have to adapt the connections, so to evaluate the behavior of the network in an epoch in time during the life of the robot. So what we can do is to observe the outcome of the coupling of this particular coupling sensor nodes and nodes actuators controlling the robot, evaluate it by means of a situated utility function, and this provides the evaluation for that particular connection, instance of connection. Then we change the connection slightly, more or less. So it's basically a minor variation of these connections, and we evaluate again the robot, and the robot compares the two evaluations and keeps the better one among the two. So this is, let's say, roughly the basic mechanisms. Then there are some variants. Moreover, the point here is to exploit some kind of internal dynamics of the network. So the network we used must have loops, feedbacks, so classical situations in which the usual learning algorithm might fail. So that's why we use this simple mechanism. I don't know if I answered your question.
Yeah.
Okay.
Okay. Thank you.
Thank you.
Thank you very much.
Any other question? Doesn't seem so. So I wish to thank Andrea again. Thanks for this presentation.
Thank you. Thank you.